again. This is going to be part number 6 of collective communications in MPI, and we're going to continue from where we left off last time. So let me find this PDF. We're going to talk about global reduction operations. The functions in the section perform a global reduce operation. It can be a sum, a maximum, or any logical sort of operator across all members of a group. The reduction operation can be either one of the predefined list of operations, or it can be a user-defined operation. The global reduction functions come in several flavors. A reduce operation that returns basically the result of the reduction operation into one process, that is the root process. We have an all reduce flavor that returns the results into all members of the group. And we have two scan operations as well. We call them also prefix. In addition, a reduce scatter operation also combines both reduction functionality and scatter operation functionality. So let's jump into the first and the most simple sort of reduction operation, that is MPI reduce. The arguments, it takes the send buffer, receive buffer count. We have seen this pattern a billion times already, data type. It takes an OP, which is sort of the reduce operation. It is also a handle. And then there's also a root here, which is sort of significant. Why? Because this flavor, this MPI reduce, returns the result of the reduction operation into the root, that is the root process that gets the result. And com is basically the context of communication. So either it's going to be intra-communicator or it's going to be an intercommunicator. And also note that this receive buffer is only significant at the root process. So we have an example for that one. It's MPI reduce.c. Actually, we got to go to reduce ops and into blocking and MPI reduce.c. So this is the example. It's a very simple one. But let's read these sentences first. If communicator is an intra-communicator, the MPI reduce combines the elements provided in the input buffer of each MPI process in the group using the operation OP and returns the combined value in the output buffer of the MPI process with rank root. The input buffer is defined by arguments send buffer count data type. The output buffer is defined by arguments receive buffer count data type. So this means that both of the receive and send buffers, they have the same number of elements with the same type. The routine is called by all group members using the same arguments for count data type operation, root, and communicator. Thus, all MPI processes provide input buffers of the same length with elements of the same type. Okay. So we're going to pass this. One important thing, or let's say characteristics of the operation or the OP, is that it is always assumed to be associative. All predefined operations are also assumed to be commutative. Users may define operations that are assumed to be associative but not commutative. The canonical evaluation order of a reduction operation is determined by the ranks of the MPI processes in that group. However, the implementation can take advantage of associativity or associativity and commutativity. Oh, commutativity, that's a hard word to pronounce for me. In order to change the order of evaluation. This is also very important. Okay. I think we can take a look at the example right now. So, these things, you already know what that is. You're not bound to only send one buffer. That is why I mentioned as an array of stuff. So send buffer in this case is just two integers, an array of two integers. And receive buffer is also an array of two integers. And we're going to sort of uniquely populate those send buffers with the rank of each process. And then we call MPI reduce with the respective arguments. That is actually send buffer, receive buffer. This is the count. It's going to be 2 because we have an array of 2 elements. And then the type of those elements are integers. And this time we want to perform, so this is the operation. This is one of those predefined operations that we're talking about. So these are those predefined operations that we have. We have MPI max. It sort of gets the maximum of all the sort of input values. And then we have minimum, sum, product, L and, that is the logical and, B and, with this is the bitwise and then all the way you can take a look at the list here. So we have picked here in this simple example, it basically computes the sum of all of the ranks, because the send buffer is also rank, and both of these buffers are going to be filled up with rank. So the final result is going to be the same. And then finally, because this MPI reduce is a blocking call, so we are 100% sure after this function call returns that we can safely sort of access the results in the root process. And this 0 is actually the root process that gets the result. So that is why we print the receive buffer only at the root. And then this is the communicator. Of course, we're talking about the intra-communicator sort of scenario. That is what we get this MPI come world. So let's go with MPI cc MPI reduce.c and MPI run. With four processes, we have 0, 1, 2, and 3. And the summation of 0, 1, 2, and 3 is going to be 6. So that is why we have sum of 6 and sum of 6 in both 0th element and the first element. And note that this is the root communicating with us. The next thing is, this is probably one of the interesting sort of operations that you can use. This is MPI MAXLOC and MINLOC, which basically combines two things. So the two operations MINLOC and MAXLOC are discussed separately in this section 694. We're going to see it in a second. Actually, let's just jump into that. Where is that section? Yeah, here. So this MINLOC and MAXLOC, you see, is used to compute a global minimum and also an index attached to the minimum value. So it's going to find the minimum, and it's going to also attach an index to that value. It is sort of like that. We had an example in C++ series about these. If I'm not mistaken, we had like keys and values associated to that. But MPI standard uses some different naming for that. It uses the sort of value and index, not key and value, but it uses the value and index, these two things. And MAXLOC also computes a global maximum and an index. Okay, one application of these is to compute a global minimum or maximum and the rank of the MPI process containing this value. So this operation can be defined like this. Imagine that you have a U and V, so these are your values, and you have an I and J, these are so those indices. So I and J are going to get sort of populated with the rank of the processes, because we said that we want to have the rank of the process containing that value. U and V are those values, and this sort of O-shaped operator here is the operator sort of acts on these two elements. And then this W is going to be either U or V, and we're going to use the max because we're using MAXLOC. So it's going to be the maximum of U and V. So if U is greater than V, then the index is going to be I. If U is smaller than V, then the index is going to be J. But if both of them are equal, then this means that it always sends the minimum of the indices I and J. So this means that the first occurrence of maximum is always returned in this case. And for MINLOC is also the same, but again, the first occurrence of the minimum is going to get returned. So we're going to see an example here as well. So let's take a look at it. That's MPI reduce, I think, MAXLOC. Yes. So imagine that we have a struct here that's going to be our data. It contains a value, and the second argument is going to be a rank. And so I'm going to have a send buffer and a receive buffer. So I'm going to populate the send buffer value with the rank of, so this thing is going to get executed by each and every process. So I'm going to have my value to be my rank, and I'm going to have my rank to be rank. So you can also initialize it with something else. Let me maybe put something else here so that we don't end up with the same result. So let's say rank times 2. This is how we initialize the value in each process. And then we call this MPI reduce, and instead of type, we pass in MPI 2 int. So if you go back here, you're going to see that okay, in order to use MINLOC and MAXLOC in a reduction operation, one must provide a data type argument that represents a pair. This is what I was talking about, a value and index. So it's sort of similar to that key and value that we had in C++, but this is completely different. So you're going to have a value, an index. So and the data type that you're providing must sort of have this it can have these sort of predefined data types, such as float int. So this means your value is sort of float, and your index is sort of integer. Your value is double, your index is int. This is how you can interpret that. And MPI to int, this is what we use in our example. It means that you have int and int. So that's because in our data structure, we had an integer value, and we had also an integer, which was the rank of the process. And we used the MPI MAXLOC, and this is our root process, and the root process is going to basically print the maximum of the data that we have. So data is basically 2 times the rank of each process, and then the location of that maximum. Where did that thing happen? In which basically rank of process that maximum happened is going to get returned to us as well. So that's the MPI CC, MPI reduce MAXLOC, and MPI run. In 4 processes, of course, you're going to have 0, 1, 2, and 3. And process number 3, the data that it has is 3 multiplied by 2, which is 6. That's the maximum among all of them. And the location, or the process sort of process number that this maximum happens, is process number 3, of course. So that was an example about this mean and max lock. There's a short sort of hint here about signed characters and reductions, and that is these types, that MPI signed character and MPI unsigned character, can be used in reduction operations. But note that MPI character, MPI W character, the white character, or MPI character, which is these variations, they represent printable characters, cannot be used in reduction operations. These things cannot be used in reduction operations in a heterogeneous environment. MPI character, MPI W character, and MPI character will be translated so as to preserve the printable characters, whereas MPI signed character and MPI unsigned character, they will be translated so as to preserve the integer value. So this is super, super important to know. And then, yeah, this is stuff we already talked about it. These are different operations that we have. And you have like different data types. These are the predefined data types. These are the examples. We had our own examples. We have seen an example about MinLoc and MaxLoc. Now we can proceed to the next session. We don't have any example for this one, but you basically can query for the value and index. This is in conjunction with what we had in MaxLoc and MinLoc, because you have the values and indices, that pair. We don't care about these examples. That was Fortran example. We don't care about this example as well. So the next section that we care about is user-defined reduction operations. So we have seen, for example, MPI sum. You can use MPI max. Those are predefined operations, but you can also have your own reduction operation. You should use MPI OP create to create your own user function. So it has a user function, that's user-defined function. It has a commute, that's sort of an integer in C. You can see it's integer, int commute. It's an integer basically representing true or false. True is if it's commutative, and false if it's basically not commutative. And we already know that we said all of the operations are assumed to be associative. So that's why we don't have any sort of true or false for associativity, but we have it only for commutativity. And then we have OP, which is going to be the output of it. That's going to be the operation handle based on your user function. So that's how it looks in C for C bindings. You can also have a _C version, which takes this _C user function. That's so you have like 2 versions of it for C bindings. Okay, we have also one example of this one, but before maybe jumping into that, again, we mentioned that the user-defined operation is assumed to be associative. If the commute is true, then it means that the operation is both commutative and associative, and if it's false, then it's going to be only sort of associative. Okay, then the argument user function or user FN and user defined function, which must have the following 4 arguments. So if you want to define your own user function, then you need to always have these 4 arguments. You need to have an invec, an inoutvec, a length, and a data type. So MPI user function also supports large count types and separate additional MPI callback function prototype declarations in C. Those are which are suffixed with those underscore C, and for Fortran we don't care. So far, what did we learn? We learned that MPI OP create has basically these 3 arguments, and then for argument number 1, which is the user function, you need to provide 4 arguments. Those arguments are invec, inoutvec, and length and data type. Okay, we're going to see how we're going to populate that in a second in an example that we have. Then we have, it says let u0 up until u length minus 1. In general, it's going to be 0 to length minus 1. It's going to be the length of length. Be the length elements in the communication buffer described by the arguments invec, length, and data type when function is invoked. And let v from 0 to the index of length minus 1 be length elements in communication buffer described by the arguments inoutvec, length, and data type when the function is invoked. Let w be the length elements in communication buffer described by the arguments inoutvec, length, and data buffer, or data type. When the function returns, then we have the result in the w, which is going to be that u, and then this, this circle, which is that sort of operation between u and v, between these and these. So where this O is the reduce operation that the function computes. Okay. And let's see what important stuff do we have here. No MPI communication function may be called inside the user function. MPI abort may be called inside the function in case of an error. So this is also a small hint here, a side note. And then we have sort of one example here, which we're going to jump in to see our own example here. So let's see, what do we call it? I think it's this one, yeah. Vim MPI op create .c. Okay, so we have taken the same example that was defined here, exactly. This is MPI op create. This is an example of a user-defined reduce operation. We basically implement the same stuff here, but this example is not complete. So it's like portions of the code that they put there, but the full example, you can see it here. This is exactly the same mimic of the thing that we have here. So it's going to be used for data types of complex numbers. So suppose that we have a general data type of complex number, which is constructed by 2 double members, one the real part and the other one is the imaginary part. So our user-defined reduce operation is going to be defined like that. So we're going to calculate the product of all of the complex numbers in all the processes that we have. And that's going to be, as I said, we're going to have 4 arguments. One is going to be invec, the next one is going to be inoutvec, then we have the length, and then we have the data type. So what we're going to do here is we define a complex number, and then we define sort of an in, because the type of these invec and inoutvec, they're void stars. But since we want to work with these data types of complex numbers, we're going to sort of do this casting. So we cast it to, and we're going to have in instead of invec, and we're going to have inout instead of inoutvec. And what we're going to do is basically for the length, this is a for loop, we're going to basically do the multiplication. So if you, for example, have a plus bi, that's going to be the complex number 1. The complex number 2, which is going to be c plus di, and then you try to multiply these two, then you're going to end up with this pattern that the real part of the first one times the real part of the second one minus the imaginary part of the first one times the imaginary part of the second one. So this is going to be the real part of the result of the multiplication of two complex numbers, and the imaginary part of the basically the result of the multiplication of two complex numbers is going to be the real part of the first number multiplied by the imaginary part of the second number plus the real part of the second number multiplied by the imaginary part of the first number. You can simply do it on a piece of paper, and then you understand what I mean. So this is the result of the complex multiplication, and then you need to always rewrite the result into this inoutvec. So that is why the signature is inoutvec, because it's going to change. And once we do the multiplication and the results are stored there, then it's going to get basically assigned with the result of C, and it's going to be rewritten into this inoutvec. So that is why we have this signature of inout here. And then, of course, you need to do it. You need to plus the pointer as well. You need to do it for all let's say, processes involved, how many elements of those complex numbers you have. And this is our main function. These things, you already know what they are. And so our data type is going to be complex type. And it's simply, we're going to use, so if you haven't watched data types in MPI, I do encourage you to go back and watch the episode about data types in MPI, because we are using this MPI sort of type constructor, MPI type contiguous. So we're going to have two elements, and those two elements are going to be doubles, and we pass in this data type to basically represent this complex structure, two doubles. That is why we have these two elements here and two doubles. And this is going to get reflected basically into this MPI data type. Now we have complex type that we can use in our communication operations. And then remember that you need to always commit your type. So that is why you commit your type here. And then we need to also define our user-defined operation. For that, you need to use this type, MPI OP. That's going to be a complex product. We name it like that. And then we're going to use the MPI OP create. That's the sort of operation or sort of the function that we had in the standard that we had to use to define our user-defined operation, reduction operation. Here, we pass in product. That's 1. It means that it's going to be commutative because it's a product. So A times B is the same as B times A. So product is also commutative. So the order of multiplication doesn't matter. And then we pass in this complex product, which is the operation that we have. And finally, this product here, which is send, here is the user-defined function. So that's the first argument, user-defined function. The next argument is whether it is commutative or not. And the last argument is basically the operation that you want to pass in there as an output. You're going to get it. So now we create an array of 10 complex numbers for each processor. That's an array of 10 variables of complex. And then we try to initialize for each process with respect to rank +1. I put a +1 here because rank 0 has the value of 0 and then multiplication of 0. Whoops. So we reached the mark of 25 minutes or so. I'm going to continue and finish this example, and then we're going to continue in the next part. So we populate it with rank +1 because, as I said, it's going to be process number 0 is going to have value 0, and we don't want to have 0 in multiplication because we're going to end up having 0. Okay, so the result is going to be null, and then rank 0, the root process, is going to allocate the proper space for that because we know that reduction operation, the root process gets the results. So he is responsible for allocating proper spacing for the result. And then MPI OP commutative. So query. So we haven't seen this query. I'm not going to comment on this. Let's have this one there. We're not going to comment on that. We're going to see it in the rest of the document. Let's use our basically user-defined reduction operation. So we pass in our array, and this is our result. This is going to basically get populated in the root process. And then we have how many elements? 10 complex numbers we have. The type is complex type, which we have basically constructed it with that MPI type contiguous. And then we have complex product. That's our user-defined operation, reduction operation. And this 0 is basically the root process rank. And then MPI COM-world is sort of the context of communication, which is an intra-communicator scenario right now. And then after doing this, we know that the buffer is safe to be read. And process number 0 is going to print the result, the real part and the imaginary part of the complex number multiplication. We don't forget to, because result was allocated dynamically with malloc, we need to free that. And we have committed our data type here, complex type. We need to always use this MPI type free. Again, watch the episode about data types in MPI. And then finally, you need to also free your basically user-defined operation here. So let's run this example, MPI CC MPI OP create.c and MPI run. So this is going to be, if you do the multiplication on a piece of paper, this is exactly what you will end up getting. Okay, so I'm going to continue the next part.